Myself, M. Karthik Kumar Reddy, working as an assistant professor in Nalla Narasimha Reddy Education Society's group of institutions in the Department of Civil Engineering in Foundation Engineering subject in Unit 4, that is shallow foundations. So friends, in the last lecture I have discussed about basic principles of shallow foundation, what are the different types of shallow foundation, and how the failures of the soil mass takes place, whether it is a general shear failure case or it may be the local shear failure case or punch shear failure case. I have also discussed about the Terzaghi's bearing capacity theory, which is based on the strip footing which is resting on the soil mass of infinite extent. This is taken as the case of plane strain problem. Now if you see this figure, now in this figure you can see that there is a column and foundation. This foundation transmits load on the soil underneath it. The foundation is placed at a depth df below the ground surface. Now when the loads are transmitted through the foundation onto the soil, and as the base of this foundation is rough, there is an active wedge which is formed below the foundation, and the angle which it makes the horizontal is phi. The Terzaghi's theory, and when this foundation becomes the part of this particular foundation, and in this, when this wedge passes the soil mass, you will find out that the shearing stresses are developed in the soil, and the movement thus is resisted by the soil mass underneath it. Now you can see here there are two zones numbered as zone 2 and zone 3. This is the zone of radial shear, and this is the third zone which will be giving the passive resistance. Now the free body diagram of this particular wedge is shown in the next figure like ABJ, in which B is the width and the load which is applied, that is actually the net ultimate bearing capacity of the foundation. The forces to which it is subjected on the AJ and BJ sides, these are the resistance which are offered due to cohesion, and these sides are the rough retaining walls, and the forces which are acting it as pushing. So the forces are the passive resistance offered by this. You can also know very well that this is the shearing surfaces do not go behind the horizontal surface at the base of the level, and it means it is the shearing resistance which is not considered of the soil depth df, and its effect is only taken into account. So this is the Terzaghi's bearing capacity analysis, and on the basis of this, while considering the static equilibrium of the wedge, we have found that the bearing capacity equation in the general shear failure case will be given by Q ultimate equal to CNC plus Q naught NQ plus Q ultimate will be equal to CNC plus Q naught NQ plus 0.5 gamma B n gamma. And for local shear failure case, C dash will be equal to 2 by 3 C, and tan phi dash will be equal to 2 by 3 tan phi. The bearing capacity factors may be considered as NC, NQ and N gamma, may be read from the table, which are known as bearing capacity factors NC, NQ and N gamma may be read from the table. And the expression for this, now in the case of local shear case, when the failure is in the local shear, then there are some modifications made, like C is replaced by 2/3 of C, and in order to determine bearing capacity factors NC, NQ and N gamma, which are based on the angle of shearing resistance of the soil, then the angle of shearing resistance is determined by phi dash, where when this phi dash may be determined as tan phi dash is equal to 2/3 of tan phi. It means that phi dash is the shearing resistance for the local shear failure case, and all those bearing capacity factors can be read from the table. Correlations are also available, but for read use we can use these tables. Now you will find that there is no bearing capacity equation available to account for the transition from the general case, and from the general shear failure case will take place when the phi value is greater than 38 degrees, whereas for the local shear failure case that phi is less than 28 degrees. but between 28 and 38 degrees there is no bearing capacity equation. So in order to take into account the transition peak in 1974 have given the curves for NQ, N gamma and which automatically account for the mixed state of local and general shear failures. Now when we are going to discuss about the general bearing capacity of shallow foundations, now several investigations have refined the solutions suggested by Terzaghi, including Mehraf in 1951 and Morgenstern in 1953 and Bala in 1962. Now all the solutions suggest that the bearing capacity factors NC, NQ do not change much. However, N gamma vary widely, mainly due to the assumption of the wedge shape located directly below the footing. It means this is the elastic wedge which is found below the foundation. Now model test has been shown that the sides of the wedge ABJ, which makes an angle of 45 plus 5 by 2 instead of 5 as suggested by Terzaghi. Now this type of failure, now here you can see once again, as far as the failure zones are concerned, or the wedge zone is considered in the case of Terzaghi 1, 2, 3, which was making that 5 in the case of Terzaghi, and now it is 45 plus 5 by 2 in the case of another theories. 5 in case of Terzaghi and 45 plus 5 by 2 in case of another theories. Now these are the particular, by this particular observation has been obtained. The equation is in the same general form as that given by Terzaghi. However, the bearing capacity factors are not the same. Equation is same, but bearing capacity factors are changing because of the inclination of the wedge. However, Terzaghi bearing capacity equation yield good results for all practical purposes. That is why you will find that the Terzaghi's bearing capacity factors, that is the Terzaghi bearing capacity equation, has been developed for a strip footing of size B, which is resting at a depth gamma df. Now in these particular correlations or the equation can be extended in the case of circular foundations or in the case of square foundations. In the square foundation, Q ultimate will be equal to 1 by 3 CNC plus QNQ plus 0.4 gamma B and gamma. Whereas in the case of circular foundation, it will be equal to Q ultimate will be equal to 1.3 CNC plus QNQ plus 0.3 gamma B and gamma. For circular foundation, we are going to take it as 0.3 gamma B and gamma, and for square foundations, we are going to take it as 0.4 gamma B and gamma. You can see from here that C is replaced by 1.3 C and 0.5 is replaced by 0.4. Similarly, the case for circular foundation, in which this is 1.3 CNC plus QNQ 1.3 CNC plus QNQ plus 0.3 gamma B and gamma. And now in the case of rectangular foundation, Q ultimate will be equal to Q ultimate is Q CNC plus of 1 plus 0.3 B by L plus Q into NQ plus 0.5 gamma B and gamma of 1 minus 0.2 B by L, where B will be equal to width or diameter and L will be equal to length of foundation. And coming to the Skempton's bearing capacity factors, for saturated clayey soils, Skempton's 1951 has proposed the following equation for strip foundation. In this, Q ultimate will be equal to CNC plus gamma df, whereas Q net ultimate will be equal to Q ultimate minus gamma df. While doing the problems, we have to be careful while solving Q ultimate and Q net ultimate. Finally, Q ultimate will be equal to CNC, which will be equal to Q ultimate by 2 into NC, where Q ultimate will be equal to Q ultimate is considered as unconfined compressive strength of clay. Suppose if we assume factor of safety is equal to 3 and NC is equal to 6, for all practical purposes, QNS for strip footing may be written as Q nets can be represented as QU by 2 into NC by F, which will be equal to QU by 2 into 6 by 3, which will be equal to Q ultimate, that is ultimate. This is the graph which we have drawn after three types of footings, that is circular, square and rectangular footings. So here there is a chart which is shown by referring time. These chemicals bearing capacity factors are used for clay soils. Now in the case of, you can see from this the plot, that is a lower and upper limiting values of NC for strip and square foundations may be written as follows, like for different types of foundation and for different ratio of df by b. For the strip footing it can be 0, for 0 it will be 5.14, if it is greater than or equal to 4 it is 7.5, for square footing it is 0, if df by b is 0 then it is 6.2, and if it is greater than or equal to 4 it can be taken as 9. The equation for rectangular foundation may be written as NCR will be equal to 0.84 plus 0.16 into B by L of NC into S, where NCR will be equal to NC for rectangular foundation and NC is equal to NCS will be equal to NC for square foundation.